Welcome to the Hydrogen Engineering Fundamentals module. Before we discuss fuel cell, electrolyzer, storage tank or hydrogen vehicles, we need to build a strong engineering foundation. One of the biggest problems in the hydrogen industry today is misinformation. Some people believe hydrogen will solve every energy problem. Others believe hydrogen is too dangerous or impractical to ever succeed. As an engineer, we must avoid both extreme levels. Engineering is not about the belief. Engineering is about the understanding physics, chemistry, economics, and system design. This module is called a reality check because our goal is to understand hydrogen exactly as it is. Not better, not worse, just accurately what is the hydrogen. We will start at the atomic level and gradually move toward the real world engineering application. By the end of this module, we will understand why hydrogen behaves differently from other fuels, why storage is difficult, why safety systems are so important, and where hydrogen truly creates value. Most importantly, we will begin thinking like a hydrogen engineer. Let's begin with a simple question. What exactly is a hydrogen? Many people use the word hydrogen is automatically means a clean energy. However, hydrogen itself is neither good or bad. Hydrogen is simply a material with specific physical and chemical property. As engineers, we must move beyond the buzzwords. The goal is not memorize the hydrogen facts. The goal is to understand how those facts affect a real engineering system. So for example, if hydrogen is very light, what does that mean for a storage tank? Second question, if hydrogen is the smallest molecule, what does that mean for a leakage? If hydrogen contains a large amount of energy per kilogram, what does that mean for transportation? Every property has an engineering consequence. That consequence influences system design. Throughout this course, I want you to continuously ask one question. What does this property mean in the real world? This mindset separates engineers from other people who simply memorize information. Remember, hydrogen is not a magic. Hydrogen is a tool, and like an engineering tool, it must be matched to the correct application. To understand hydrogen engineering, we must start at the smallest possible scale, the atom. Hydrogen is the first element in the periodic table. It is also simplest element. A hydrogen atom contains one proton, one electron. Most common form, no neutron. This makes hydrogen unique because hydrogen is so light, its behavior differs significantly from large atoms and molecules. However, in a practical engineering system, hydrogen does not exist as an individual atom. Instead, hydrogen atoms naturally combine in a pair. This creates a molecule hydrogen, which we separate as H2. Used in hydrogen storage tanks, fuel cells, pipelines, refueling stations, industrial application. The molecular weight of hydrogen gas is approximately 2 grams per mole, making it the lightest gas commonly encountered in an engineering system. This extremely low molecular weight explains many of hydrogen's unique characteristics. It rises rapidly, it diffuses quickly, it can leak through very small openings, and it behaves differently than hydrocarbon fuels. Study in this course ultimately start with this simple atomic structure. It's one of the most important concepts in hydrogen engineering. Hydrogen is not a primary energy source. Hydrogen is an energy carrier. Let's understand the difference between both of these. Coal is a primary energy source. Natural gas is a primary energy source. Crude oil is a primary energy source. These materials already contains usable energy when extracted from the earth. Hydrogen is different. Hydrogen does not exist freely in a large quantity. Instead, hydrogen is usually bound to other substance. For example, water contains hydrogen bonded to oxygen. Natural gas contains hydrogen bonded to the carbon. To obtain usable hydrogen, we must first spend energy. We use heat or electricity or chemical reaction. Only then obtain a pure hydrogen. This hydrogen acts much like a battery. Energy is invested during production, energy is recovered during use. This concept is extremely important. Hydrogen's environmental impact depends entirely on how it's produced. If hydrogen is produced using renewable electricity, emission can be very low. If hydrogen is produced using fossil fuels without carbon capture, emission can be much higher. Therefore, engineers must always ask one question: where did the hydrogen come from? The question is often more important than the hydrogen itself. Arrive at one of the most fascinating concepts in hydrogen engineering, the energy density paradox. Let's start with some numbers. Hydrogen contains approximately 120 megajoules of energy per kilogram. Gasoline contains approximately 44 megajoules per kilogram. Diesel contains approximately 45 megajoules per kilogram. Modern lithium-ion batteries typically store around 1 megajoule per kilogram. At the first glance, hydrogen appears unbeatable. Per kilogram, hydrogen stores almost 3 times more energy than any gasoline, and over 100 times more energy than a batteries. This sounds very revolutionary. However, there is a catch. This number describes energy per unit mass, not energy per unit volume. Hydrogen gas occupies a tremendous amount of space. A kilogram of hydrogen contains lot of energy, but it requires a very large volume unless it compressed or liquefied. This creates the central paradox of hydrogen engineering. Hydrogen is a very good by weight, but hydrogen is very challenging by volume. Almost every major engineering challenge in hydrogen system can be traced back to this single fact. Storage tank, compression system, transportation infrastructure, vehicle packaging, all are influenced by the hydrogen's low volumetric energy density. This is why understanding energy density is one of the most important concepts in the entire hydrogen industry. Discussion about hydrogen energy density. In the previous slide, we learned the hydrogen contains approximately 120 megajoules of energy per kilogram. That sounds incredible. However, engineers cannot design systems based only on a mass. We must also consider a volume. Imagine carrying 1 kilogram of feather and 1 kilogram of a steel. Both have the same mass, but they occupy very different amount of space. Hydrogen behaves in similar ways. At normal atmospheric pressure, hydrogen gas occupies a very large volume. In practical terms, storing hydrogen in its natural gaseous state would be require enormous tanks or big tanks. This is why storage becomes one of the most important engineering challenge in this hydrogen economy. To make hydrogen useful, engineers must either compress it to very high pressure or cool it to extremely low temperatures. Every storage solution involves trade-offs between the 3 points: safety, cost, energy consumption, weight, and system complexity. Understanding these trade-offs is essential because storage often determines whether a hydrogen application is practical or not. Slide 7. There is so much space, compression becomes essential. Compression simply means squeezing hydrogen into a smaller volume. Modern fuel cell vehicles typically store hydrogen at a 350 bar or 700 bar. To understand how high this pressure is, consider that a car tire normally operates about a 2 to 3 bar. A 700 hydrogen tank stores gas at hundreds of times greater than the pressure. Right? Hydrogen can be stored in a smaller space. However, free compressor require energy. Depending on operating condition, compression may consume between 10 to 15% of the hydrogen energy content. This means engineers must carefully balance storage efficiency against the energy losses. Comps also be designed for a long-term reliability because they operate under the demanding conditions. In many hydrogen facilities, compressors are among the most critical piece of equipment. Slide storage density is a liquefaction. We cool it until it becomes liquid. Hydrogen liquefies at approximately minus 253 degrees Celsius. This is one of the most coldest temperature used in industrial engineering. By converting hydrogen into liquid, its storage density increases dramatically. This is a partial application, long distance transport, large scale storage, and future aviation concepts. However, liquid hydrogen introduces new engineering challenges. Maintaining cryogenic temperature requires specialized isolation systems. Even a small amount of heat entering the tank can use the hydrogen to evaporate. This process is called boil-off. Liquefaction This liquid hydrogen process itself is also energy intensive. In some cases, liquefaction can consume up to 30% of hydrogen storage energy. Therefore, liquid hydrogen improves storage density but increases system complexity and operating costs. This is a classic engineering trade-off. Slide 9. Discuss safety become a major topic. Many people immediately ask, is hydrogen dangerous? The correct engineering answer, hydrogen is neither safe nor dangerous by itself. It depends entirely on how it is managed. Every energy carrier risk. Petrol is flammable, natural gas, high voltage electricity is dangerous. Hydrogen is no different. What makes hydrogen unique are its physical properties. Hydrogen is extremely light, it disappears rapidly when released, its ignition energy is very low, and it's burned differently than hydrocarbon fuels. Because of this property, hydrogen systems require specialized safety strategies. Engineers use leak detection sensors, pressure relief devices, ventilation system, emergency shutdown control, and rigorous testing standards. And high testing standards. Modern hydrogen systems are designed to according to the principle of risk management rather than the risk elimination. The goal is not to create a system with a zero risk. The goal is to understanding risk and control them with effectively. Slide 10. Let's look at how engineers actually make hydrogen systems safe. The first layer of safety is a prevention. This includes proper material selection, high quality manufacturing, robust system design. Second layer is a detection. Hydrogen sensor container for leaks. If abnormal conditions are detected, the control system responds immediately. The third layer is a protection. Pressure relief devices prevent dangerous pressure buildup. Automatic shut-off valves isolate affected section of the system. The fourth layer is a mitigation. Ventilation system safely disappear leak hydrogen. Emergency procedure ensure controlled response during the abnormal events. This layered approach is known as a defense in depth. It is widely used in aerospace, chemical processing, nuclear engineering, and hydrogen system. One of the most important lessons in engineering is that safety is not a single component. Safety is a system. Every valve, every sensor, regulator, tank, and control algorithm contributes to overall safety reliability. As we move deeper into this course, you will see that successful hydrogen engineering depends just design as it